So continuing on the previous question in regards to having two vectors, one of which is 3, 4. So I'm going to draw the vector 3, 4. So 3, 3 to the right, and 4 up. So that's my first vector. Let's call that vector A. And the second vector is 8, 1. So 8 to the right and 1 up. So those are our two vectors. And in the previous question, I asked you guys to figure out or try to calculate the magnitude of the projection of A on B. So let's just recap that. So this is my vector A, and this is my vector B, and you were asked to draw and find the magnitude of A on B. So what this means is, let's use a different color, let's use red. So imagine it was like flashing down on the B, alright, so the area that's not affected is going to be from here all the way to here, right underneath the tip. So I'm going to draw a little right angle triangle just to indicate that this is a vector of interest. Now, our goal is to find the magnitude of this. Now, in order to find the magnitude of this, what we know about this triangle, since I did draw a triangle, is the angle in between. All right, we don't know this. If you want to find this angle, you could find the magnitude of this, and maybe this, and then use cosine law to find this. But we're going to actually find this angle, or attempt to use this angle using what we learned before called the dot product. So if you recall here, this is the dot product. So dot product will give you the magnitude of this times cosine. All right. But the question is, we're interested in this red line here, which is connected to a right angle triangle. Let's actually make this more nicer look. Oh, nicer looking. So let's just say we got this angle from the dot product. Then what? How can we find this? So we actually have the magnitude of this, all right, which is using Pythagorean theorem. So the magnitude of A, in our case, is going to be, I believe, you use the 3 square plus 4 square, and you end up getting 5. So this is 5. So we got this is 5. Now the thing is, if we had this angle, let's just say we actually figured this number out, all right, how do we find this? We can use what we learned in grade 10, or what you were taught in grade 10, the cosine. So cosine theta is equals to, let's call this the magnitude of A, and this is the adjacent. So we're going to call this, in the textbook they like to use ON for some reason. So we'll call the projection ON, the scalar projection over the magnitude of A. So this is adjacent over the hypotenuse. And we know in this case it's going to be, I believe it's 5 over ON, right? Or we can actually rearrange this and solve for ON. ON is actually equal to 5 times cos theta. So I'm just going to generalize this. I'm going to, instead of calling it 5, I'm just going to go back and call it the magnitude of A, which is 5. But I'm just going to generalize this. So what's interesting about math is we can actually manipulate or modify this equation by introducing something such that we can make it more simpler. What I mean by that is I notice this side is magnitude of A and cosine, which is kind of part of the dot product. Kind of. We're just missing the B magnitude. So what I'm going to do is multiply both sides by B. So I'll use a different, so I'll put here magnitude of B and magnitude of B. Okay? And if you notice, this whole thing is the dot product. This is pretty much A dot B. And over here we have B and ON. So we're actually reformatting this. But ultimately, as I said before, our goal is to figure out the length of the red, which is the ON. So ON, I'm just going to rearrange this, A dot B over the magnitude of B. And these two things, these two pieces of information we have the component of A and B. So all I'm going to do is take the dot product of 3, 4, I dot it with 8, 1, and then I want to find the magnitude of B. So the length of this vector here, we can use Pythagorean theorem, 8 squared plus 1 squared, square root, 8 squared plus 1 squared, and we end up getting the magnitude. So if you recall, dot product, it's 3 times 8 plus 4 times 1, which is 28 over the square root of 65. So in other words, this is the scalar projection. This is the magnitude of this. Now there are other ways we can solve for this using grade 10 methods, but this method is very efficient. It's only 3 steps, and we don't need to use the inverse. We don't actually have to calculate the actual angle of this. So to generalize this, if we want to find the projection, the scalar projection of, in this case, it was, what was it? It was A on B. So A on B. We end up actually developing a general formula for this. Basically, we're going to take the dot product, A dot B, divided by the magnitude of the bottom vector. This is what it's going to be. Now, if I want to find the magnitude of the other way around, which is B on A, it would pretty much be the same. Things would be reversed, but you would find the magnitude of not the B vector, but the A vector. And if you recall, the dot product, it doesn't really matter which way you take the dot product of, because A dot B is the same thing as B dot E because they are commutative. So for 3D, it's exactly the same thing. Whatever we do in 2D applies to 3D. The only difference is there's a third component, the Z component. So, and it's kind of tough to draw a vector projection in 3D because it is 3D. So I'll do an example. So it's pretty much the same idea. If I want A on B on A, we know that we're going to take the dot product regardless. All right. I'll do both too. I'll do the other way around. So if I had A on B, we know we're going to take the dot product. All right, A dot B. I should use these vector signs as proper communication. Now the question is, what are we going to find the magnitude of? Well, one thing I usually tell my students is if whatever's on the bottom is on the bottom. So notice here A is on the bottom, so we're going to find the magnitude of A. Oh, B is on the bottom, so we're going to find the magnitude of B. So in other words, what we can do is take the dot product. The numerator is going to be the same. So 1 times 1, 1 times 2, 1 times 3. We end up getting 7. The only difference is the magnitude of the bottoms will be different. So the magnitude of A is just 1 square, 1 square, 1 square, which is 3. And this one is going to be slightly different, which is 1 square, 2 square, 3 square, which is, I believe, is 14. So they are different. The magnitudes are different. So after these couple of slides, you're able to find the length, the magnitude of the projection vector. Now what we're going to do is we're going to find next the vector projection. So the actual vector. For example, in the first example, so here we have a vector here. The question is, well, what's the Cartesian form? So ON is going to be what x and what y. Well, how much do I have to move to the right? Looks like over here it's approximately 4 to the right and maybe 0.5 according to this, kind of. But we can't depend on the graph to get the accurate answer. So what we're going to do is we're going to use some information that we know about these two vectors, the blue vector and the B vector. We know that based from our calculations that ON is 28 over root 65, which is, I don't know, a fraction of B. And we know that ON is collinear to B. All right, this statement is false. This statement means that this blue vector is exactly the same thing as the black vector, which is not true. But we know that ON is going to be a fraction. We'll call it a fraction, a constant. It could be a half, 0.5, according to this picture, maybe 0.4, 0.6. I don't know what it is. Now the question is, how can we figure out this K value? Well, one thing we can do is, we know the magnitude of the blue vector. Well, we can find the magnitude of the black vector and see what the proportion is to find this K value. So what we're going to do is find the magnitude of B. So magnitude of B, we use Pythagorean theorem, is going to be, well, root 65. So what we can do is find the proportion. All right, so over here, what we can do is, okay, we can take ON and divide it by the magnitude of B, and we can see what fraction it is. And in this case, it's 28 over root 65, and then divided by root 65, which is going to be how much? 28. So in this case, we can tell that, we can tell that ON is equals to 28b. Does that make sense? Actually, I found the mistake. When you divide this, you get 28 over 65. So in other words, we can say that ON is actually a fraction of B, and this is actually the fraction, okay? So what we can say right now is, all right, if the magnitudes are around 28 over 65 of B, we can therefore say that ON, the vector itself, is a fraction of the B vector. Now the question is, well, do we know the Cartesian form for B? Yeah, we do. It's 8 and 1. And what we can do afterwards is, well, what's ON? ON is going to be, you just have to multiply it out and you end up getting some fraction. So over here it's going to be 28 over 65, and over here you end up getting, let's just say this one. So this is the actual vector. What this means is, if you take your calculator, 224 divided by 65, let's assume it's around 3 point something. If you take 28 divided by 65, so 3 point something, this is going to be, let's just say 0.4 something. What this means is, to get this vector, you're going to move 3 point something to the right and 0.4 up, and that sort of matches our picture. So over here, 3 point something a little bit to the right and 0.4 a little bit up. So this is our Cartesian form. So from this specific example, we're going to generalize this. I'm going to go back to here. So we're going to actually change things. So if we recall, to find k, we had to find the magnitude of ON and compared it to the magnitude of B to find that proportion. What I'm going to do is just erase everything here. We don't need all this stuff anymore. So basically, this is how we got our k value, comparing the magnitudes. To find the vector ON, we're going to replace k with this fraction here. So it's going to be ON, and then you have your B vector, and you have this. And then, if you recall, how did we get ON? Well, ON, in this case, ON was projection of A on B, and to calculate this number here, we actually use the dot product divided by the magnitude. So over here, recall, I'm just going to remove this to the side here. To get ON, we actually found the magnitude of this by doing the dot product, so A dot B, and over the magnitude of, because we're A on top of B, so this would be B on the bottom. So in other words, this is the actual general, what the textbook, the formula to find the projection of scalar, so the vector projection. In other words, this is projection of A on B. So this is the general formula. Now, if I wanted to switch it around, for those students that like formulas and memorize them, I prefer not to memorize it. I prefer to use this method, the longer method, or the more, to me, logical method. But let's just say I want to switch this around. All right. So what would change would be, all right, the dot product doesn't really matter. It's still A dot B. The denominator would be, well, it wouldn't be B, it would be A. And this would all be changed not to B, but it would be all to A. So this is what the general formula looks like. And what's interesting about this is just a side note, this, do you guys know what this stands for? If you take a magnitude, if you take the vector and divide it by its own magnitude, this actually is the unit vector. And how it's relating to this is we'll discuss that in class, but because of time, we're going to end off here.